question.
Good. Can you hear me?
Yes.
Great. Well, so today we have the second part of the optimization part of this course, and we will start with a recap of what we have done at the end of the last course. And if you remember, last time we introduced the problem called, wait, cannot move the slide for some reason. Okay. Yeah, the problem called max flow. Okay, so what is the max flow? And here you see the outline. We will discuss about that. Then how to take the max flow and model the problem where we want to attack the system, so destroy some of the arcs of the network, and then how to find the worst case attack, how to fortify the system against attack, and then what is the link of all these with resilience. So the max flow problem, if you remember, is this problem where you are sending goods, anything, from a source to a terminal. And to do that, you are using some links. So the structure that we are using is the structure called network or graph. So you have nodes that are connected by links called arcs, and each arc has got some capacity that is the maximum amount of goods that you can send through that arc. This is the test case we introduced last time, and is actually the same that we are going to use today for our examples. So in this case, you have the node in red, the source node, and then you have the node in green here, the terminal. And the idea is that you want to send stuff from here to here using each link that is available here. And we also assume that every link got a capacity of 10. So you can send 10 units of whatever it is through each link. We also introduced the optimization model for this problem. If you remember, we discussed that. Again, this is not important in the sense that we don't want to focus on the details, but it's just for you to understand the logic and start to be familiar with MPOL. So just a quick recap, we have a few parameters. Remember, the parameters are the data of the problem, the numbers that we know before solving the problem. So how many nodes, what is the source and the terminal node. Then we have the set of vertices and links. We have other parameters like the capacity of each link arc, and we say that it would be 10 for each one of them. We have variables. So the variables is the number we want to know after the optimization. In this case is how much flow through each arc. And these are non-negative variables. Of course, we cannot send a negative flow, but we need to make sure it's specified. What we want to do is to maximize the total flow. This is the objective. The total flow we discussed last time is either the flow out of the source or the flow that is entering the terminal is the same. And why is the same? Because of this constraint that is the flow conservation. Everything entering one node is equal to what is going out from that node, except, of course, from the source and the terminal. Because from the source, we have nothing entering, and from the terminal, there is nothing going out. And finally, there is this constraint saying that we cannot have in any arc a flow that is greater than the capacity. So this is just a recap of what we discussed last time. And if you remember, we solved this problem with MPOL, and the objective function value was 30. And if we print the flow for each arc, you see here the results. And if we want to show the results on the picture, this means that we are sending flow on the bold arcs, 10 units each. So we are sending 10 units through this path, here and here, other 10 going from this to this, and the last 10 this way. So we are sending 30 units in total. This is the solution. Actually, I should say one of the solutions, because we may have other, what we call last time, symmetric solutions. For example, instead of sending the flow here, you can use these, and then these, and then this. and you will get the same result of 30. Now, let's move on to the next topic, that is, what if there is an attacker that wants to attack the system? But before that, is it everything clear with the max flow? Any question before we move on? Okay. So imagine now that we have this situation. There is an attacker that can destroy some of the components, in this case, some of the arcs of the network. And what is the objective of the attacker is the opposite of the objective we have. So our objective is to maximize the flow that we send from the source to the terminal. The attacker's objective is to minimize the same flow. So in other words, the attackers want to destroy the links in such a way that after destruction, if we try to maximize the flow, we get the minimum possible. Example, what happens if we destroy the link 47? Let's see in the graph. And actually, how can we do that in endpoint? So there is a command that I don't know if I gave you last time, is the let command. Let command is a way for us to set some values, right? In this case, we are saying the capacity of this arc is set to 0. What does it mean? That we cannot send anything, because we have a constraint saying that we can only send up to the capacity. But if the capacity is 0, we cannot use that arc. So if we do that and then we say solve the problem, what is the solution? You see, the solution is this, is slightly different, but the objective is still 30. If we print the solution, you will understand why. Because basically, the red one is the one that we destroyed, okay? So if you remember before, we were sending 10 units here, but now it's not possible anymore. So the solver, Cplex, found an alternative way. Instead of using these 4, 7, the 10 units that are going from 6 to 4 will now flow through arc 4, 1, 1, 2, 2, 8, 8, 7. So even though this arc is destroyed, we are able to find an alternative way to send the 10 units that are reaching node 4. In other words, this attack was not really effective from the point of view of the attacker, because it was not able to damage the network in such a way that the max flow is affected. Because remember, the objective of the attacker is to destroy the links that are bringing down the maximum flow as much as possible. Now we have the first activity. So I hope that your ample is running and everything is fine. What I ask you to do is the following, is to take the role of the attacker, okay? So what you have to do is to destroy 2 arcs. You can choose which ones. And your objective is to choose the 2 arcs such that the max flow after that is as low as possible. How to do that? You have to modify this file that you should have received. And I show you what I mean. This is the file that you should have, right? So this part here is where we can put the capacity of the 2 arcs that we choose to 0. So you just need to change these numbers, 4, 7, 2, 3, right? And you put the numbers that are associated with the arc that you want to destroy. So how do you know that? Well, if you go back to the picture, or you can use this list. These are the numbers basically that are valid. But these are basically the numbers that you find here, right? So for example, 4, 7 is 1. I want to destroy this one. I need to write 1, 2 inside the square bracket. If I want to destroy this one, I need to write 5, 8 inside the bracket. And you can destroy 2. So your objective as attacker, and you have 10 minutes for that, is to play with this file, right? And to choose different pairs of the arcs to be destroyed. And then you run this file, the maxflowattack.run, the way I told you last time. So the command, if you remember, was if you're under Mac, is from the command, the terminal import this, and then the name of this file. right? And then you click enter. If you're under Windows, you have to double click the Ample application, and then you write include this file, and then you click enter and it should run. So what you do is you change these numbers inside according to the arcs you want to destroy, and then you run these, and the result will be the max flow after on the damage network, basically. And you want to show that the number that is 30 normally is going as low as possible. So maybe some destruction will still give you 30. Some of them may give you 20, right? Or maybe lower, I don't know. So that's up to you to play. So let's come back in 10 minutes. And if you need any help, I'm here. You can ask me. I can show in the background here the picture. So you have the list of the arcs, and then you can maybe easily find the combination that you want to put in a square bracket. Okay? So I say, let's come back at, now it's 25 at 35.
Sorry, can you hear me?
Yes.
I have a question. I struggle a bit with the program. It doesn't find the data sets. So if
Did you put all the files in the same folder?
I think so, but the problem also is I have to download them manually, copy them in an editor, and save them.
Yeah, I mean, all the files that you have received should be put in the same folder where Ample is.
Yeah, but the
And
files are not to download.
what do you
So
mean
I
they're
have
not?
to open the files, copy what's inside the files, put it in the editor, and save them on the in the program.
Yeah, you can
I can't.
actually, if you use your right mouse click, you can like save it as, and then it will save the file. But indeed, it's not downloads links.
Save it as a
But
link, but
I have the same problem with running it.
It
Yeah,
is,
so if you go like to Moodle, you can click on each file with your right mouse thingy, and then you can say save as, and then it will
okay.
save the
I
file.
don't know how Moodles work there. I have no idea, but you don't need to copy paste. In theory, you should just download and
actually only can save it as a link. Maybe I need another browser, but
Yeah, but you can save it as a link, but it actually will, for me, it saves the file.
okay.
It's, I don't know, weird construction. But I think I have the same because last week I could run the file, I think by clicking it. I have Windows. But now I'm not sure how to run it. But maybe I should. So you say everything should be in the folder of Ample?
yeah, the same folder. Because when you are like you have Ample, you have Cplex, everything. Otherwise, you need to specify the location. So that's why it's easier to put everything there, so it will find everything usually.
Okay, I will try that.
Okay, so maybe we can take a few more minutes, and then we check. Okay, so did you get any result? Any lower than 30?
Not for me. Sorry.
Okay. I mean, do you mean no results or still get 30?
No results yet.
Okay. And what about you?
No, me neither. Last week I could run the file, but I think yeah, right now I'm still figuring out
Okay,
how to.
don't worry. I mean, it was just for you to play with that, but there will be another activity later we can check. I just want you to understand the idea. The idea is that the attacker wants to destroy arcs in such a way that the max flow resulting is as low as possible. Now, a rational attacker will not choose randomly the arcs to destroy, right? It will choose those that minimize the max flow. So imagine that you are the attacker and you know the network and you know that after your destruction, the other players of this game, because these are sometimes called games in game theories, are two-player games. And basically this guy, the other player, will do the best he can to maximize the flow, but you cannot possibly try all the combination, right? If I tell you that you can destroy up to 5 arcs, you cannot try all the 5 combinations of arcs and choose the best. And you run for each combination a max flow. There must be a better way, right? And this is what we are going to discuss in this section. So, a rational attacker, as I said, would like to destroy, let's say, gamma arcs. Gamma is a parameter that is how many arcs we can destroy. In the previous example, we just destroyed the 4-7. Now we can destroy gamma. And the question is, what are the arcs to destroy in order to minimize the max flow after attack? We want that the defender, this sometimes is called attacker-defender game. So the attacker wants the defender to get the worst possible max flow. And as I said, we cannot test all the options because this would be a stupid way. It's like enumerating. There is no optimization if we just list all the combinations, right? We can do by hand, basically. We don't need ample. We don't need anything. Of course, we need one code to solve the max flow, but there must be some other way. And how can we represent mathematically this problem? So this is what we are going to discuss now. So don't be afraid of this. I will explain. The concept is quite simple. Let's say there is a new variable z, and this variable is equal to 1 if the attacker destroys arc ij, 0 otherwise. So for each arc ij, we have zij, that is a binary variable, 0, 1. 1 I destroy, 0 I don't destroy. So this is a variable for the attacker. Now you remember that the max flow was, forget about this for now. The max flow was maximize the total flow and the variables were f, the flow, right? Now, for the attacker, we have this problem. It's called min-max. Min-max, why? Because first, we want to choose the variable z to minimize the flow. And after we choose z, that basically represents the attacks, arcs that we destroy. After that, the defender will maximize the flow. So here we have the action of the attacker, and after that, the defender. First, we destroy as attackers, then we maximize the flow on the resulting destroyed network as defender. And of course, we need to have another thing. We need to say that we cannot destroy more than gamma. So this constraint must enter the problem. The sum of zij less than or equal to gamma, because zij is 1 if we destroy arc ij. So if we sum these for all the arcs, these cannot exceed gamma. Is a budget, if you want, for the attacker. And finally, the question is, how do we ensure that when z is 1, when zij is 1, then arc ij is destroyed? If you remember in the first example, we say that by setting the capacity of an arc to 0, we are basically saying that we cannot send any flow. Is equivalent to destroying the arc. So we just need to multiply in the model here. Remember there was this constraint. The flow is less than or equal to the capacity. Now is capacity times 1 minus z. in such a way that if Z is 1, this is equivalent to Fij less than or equal to 0. So basically, the flow is 0. But if Z is 0, means the arc is not destroyed, then Fij is less than or equal to the capacity Aj as usual. So these are the modifications, 1, 2, 3, that we need to integrate into the optimization model that I showed at the beginning to represent this. But still, we have a minimize max. So it's a, yeah, we can add this constraint here, and then we can change the capacity constraint with this. But how are we going to solve this min max? We don't know how to do that, right? As I said, in optimization, we want to either minimize or maximize a function. How do we deal with min max? Now, the idea is that we can do that using something that is called duality. Duality is part of the theory of optimization, especially in linear programming and integer programming, not really, but I don't want to go to the details of the theoretical stuff. Just for you to know, this is the point. We can take a maximization problem, linear, and we can rewrite following some rules that are quite specific and transform into a minimization problem equivalent in the sense that if the maximization problem that is called primal has a valid optimal solution, the minimization problem that is called dual has exactly the same optimal solution. So I repeat, we can take a max problem, linear, and following some rules that are out of the scope of this course, we get an equivalent minimization problem, such equivalent in the sense that if one gets an optimal solution, the other one has the same optimal solution. How can we use this trick to deal with the min-max problem? Well, the thing is this. Because I say the max flow is very famous, the dual of the max flow got also a name and is called the mean cut problem. So the dual of the max flow is the mean cut. And this means, this is, by the way, the mean cut, how it looks like. So if we take the model of the max flow and then we apply these rules that I will not explain, you get this problem that is the mean cut. Okay? Forget about the meaning of this. Just for you to know that it can be done. You can take the max flow and transform in this. And if I solve the max flow and I solve this guy, I get the same optimal solution. So the max flow 30, if I solve this, I will get this objective function 30 as well. Why is this important? Because now we can say, well, since we cannot test all the possible disruption, we can take the problem we want to solve, remember the min max, but because the max flow is a linear problem, we can make that as a mean cut. We just show, right? This max flow is equivalent to this mean cut. So this guy here is the same as this, but what is the thing here? Now we have a mean, and a mean is a single mean. So basically we say, okay, we have a min max. The max problem inside can be transformed into an equivalent minimization problem, and the resulting mean problem, in this case, is a single minimization problem. What does it mean? It means that instead of trying to solve the attacker problem and try all the possible combination of gamma R's to be destroyed, just by solving one single problem, we get the worst case attack and the resulting flow after the attack in one shot. That is a very good result because you are incorporating the enumeration of all the possible attacks and you get a single problem. Is it clear so far? Again, I don't want to explain all the details of how you transform a problem in the dual, just for you to know that this can be done. And we need to do that because we can simplify a min max into a single mean problem. And we know how to solve this guy.
I have a
Yes.
question. Sorry, what's the CapCut function? I didn't
Oh,
get that.
sorry. It's basically the name of the objective function now.
What does it
Okay,
I mean, the
this function,
max flow has kind of a
yes,
logic. I don't see the logic by CapCut. What's that?
because this is based on what I told you, right? It's based on the transformation rules that I'm not explaining. It's just another function, but you can find information on the mean cut. Basically, it's looking at a way to separate the arcs, the network in two. So in a way, there is a meaning behind this problem that we can discuss. But for the purpose of this example, what is important is that if we take a max flow, right, and then you have the constraint and everything, this is equivalent of minimizing this capacity cut with the constraint here, and the capacity cut is defined this way. We sum over all the arcs the capacity times a variable, W, right? And now you see before we had the in the max flow, we got variables that are deciding basically the flow. They are telling us how much flow. Here is a little different. You see the capacity was in the constraint in the max flow, now is in the objective function. But again, it's not like the point here is not to understand what this problem does. The key point here to focus is to understand that when I solve this cut function, if the max flow give me 20, this will give me 20. If this give me 30, this is 30. Is equivalent in that sense, right? So maybe later, if you want, I can share with you more about the mean cut, but it's something quite common that you will find in the literature. What is the dual of the max flow is the mean cut, and then you will find the because I didn't prepare any picture to explain. But yeah.
We basically changed the algorithm to have a min-min problem where we can add up to both the minimization.
Yeah, so basically that's the idea. We need this because we need to get rid of this sequence. We only know how to solve a problem with a single min or max, not a min max. So now that we know that this is can be written like that, and min is a single min, then we can deal with that. There was another question. Yeah.
Yeah, I was wondering, since you said that we don't need to go over all possible combinations of edges.
Yes. Yeah.
Does that make this more a heuristic algorithm, or
No,
would
it's
also
still
all these
optimal. That's a nice thing. It's still optimal. The key point here is that because you see everything here is equal to, eventually this min max that we could at this stage we could solve with the enumeration is equal to this. Is not an heuristic. It's really the same result. So meaning to say, by solving this problem, if I were to test all the possible attacks, I would find the same solution. That's why it's quite cool, right? You don't even need to go through the procedure of listing everything.
Okay, clear. Thank you.
So in practice, what happens, this is the final model, is basically you see the mean cut with the changes that we discussed earlier. So these changes. So you see now that the capacity is multiplied by 1 minus z. You see the constraints saying that we cannot have more than gamma disruptions. By default, I set it to 3. And then we have the new variable z that are binary. So when we solve this problem here, and you set gamma to 3, the optimal solution will be the max flow after the worst disruption of 3 arcs. Okay? Okay, there is something else that here I didn't mention. This is a variable in the problem, right? And this is a variable. So we have multiplication between variables, and this is non-linear. But we say in this course we are dealing with linear problem, right? Maybe integer, but linear. So how can we deal with this non-linearity? Because this is W is a variable, this is Z is a variable, and then here in this objective function, we have a sum of some W times Z terms, and this is non-linear. So it's just a detail. There are ways to transform this kind of non-linearities when at most one of the variables is continuous. So in other words, because Z is binary, right, we can transform every product W times Z into a set of linear constraints, and we get the same solution. So even though this is non-linear in practice, we can make it linear and is equivalent. So this is more a technical detail. It's not really important, but in case you see this model later and you say, hey, you tell me that we are dealing with linear stuff and this is not linear, you're cheating. No, there is a way to make that linear. It's just that, again, it's more like a technical point. There is some, it's called McCormick inequalities if you are interested, but there is a way to make that linear, okay? Now the problem is, okay, assuming that this works, and I think the file I share with you is already the linearized form. So if you see a slight difference here is because of this point. What happens when we try to solve these with different values of gamma? Now, I run the test and I tell you what are the results. If gamma is 0, meaning we cannot destroy anything, the result is 30. Is what we expect, right? 30 is the result that we got when we solved the usual max flow problem. So if we want to solve the problem with the worst case disruption, but we can destroy nothing, we should get the same solution, right? If we say that we can destroy one arc, then the result is 20, and the arc destroyed is S4. If we say we can destroy up to 2, actually 2, the flow goes to 10, and these are the arcs that are destroyed. And when gamma is equal to 3, so we just need to destroy 3 arcs so that the flow is 0. So remember the example at the beginning when I say that if we destroy arc, I think 4-7, the flow was 30, so it was not a smart way for the attacker. This is telling us that you can do better. There is a better arc to destroy so that the flow after that is 20. Is it something we expect? Notice that every arc we destroyed involved the source. What does it mean? This is when we destroy 3 arcs. If you think about that, if I can destroy 3 arcs, well, I can just destroy the arcs that are going out from the source, and I cannot send anything, right? So of course, if I can destroy only 1, and I destroy these, I can only send 10, no more than 20. If I can destroy 2, I can only send 10, and if I destroy 3, I can send 0. So it makes sense that the arcs destroyed involve the source, right? So I would say yes. This is something that we should expect. You can say, well, what if I destroy arcs entering here? Is also an option. But in this case, we have 4 options to reach this and 3 options to send that. But we will see later. I think at this point, is there any question? I mean, is it clear the logic of what solving the attacker problem is doing? It's trying to say, hey, let me destroy the arc such that after that, when you try to solve defender, the max flow, you get the minimum flow. And then by using duality, we can get this result in just one single problem. So all these results, I got them by solving one problem, that is this one, where, as I said, I linearize these products. This is more or less the logic.
One last question.
Yeah, sure.
So this problem has I mean, a logical solution with these three lines that we can cut. If you have a more complex solution where multiple options are like valued the same, minimize this problem would still give you only one solution. So you as the good guy don't find all the attacks with the same risk.
Okay, just to clarify, it's true that there may be different disruptions that give you the same. So of course, the optimization, as we say, is only returning one solution. There may be different but equivalent solutions in the sense that maybe there is another disruption. So imagine you can destroy two links only. I can say this and this, or I can say this and this. But in both cases, the max flow is 10. So even though I'm not showing you all the options, still the solution cannot be improved in terms of objective function. So even if I give you an alternative solution, or if an alternative solution exists, what remains is that the objective function value that I get by solving this problem is the best. If there is another solution, it will be an equivalent solution, meaning even if I change disruption, the attacker cannot do better. Sorry, the defender cannot do better. If you really want to list all of them, I think we had a question last time. What we can do is to find one solution and then change the problem to make this solution infeasible. So maybe first you find this one, right? And then you say, okay, I want that these and these cannot be destroyed together. Then maybe, okay, I find these and these. Right, and then you can run another one. So there are ways by solving other problems where you can find the solutions that are symmetric, or there may be some setting in Cplex to return other solutions. But even though you cannot see all of them, what is important to understand is that the objective function is the optimal one. It's not that because I don't show you all the disruption, one of them could give you a better solution. No. All of them, like if I tell you that the max is 10, it can be this one, or it can be this one, it's still 10. Or it can be this and this, right? Still 10. So if this is what I destroy, you can do whatever you want. The max flow is 10. If I choose an alternative but symmetric equivalent solution, again, do what you do. Maybe what you do is different as defender, but still you cannot send more than 10. So you may have different follow-up strategies, but the max flow that is our performance cannot improve.
Thank you.
Yeah. So I think at this point we can have the pause, and then we go to the next level. That is, what if the defender can do something before the attacker? So instead of the attacker-defender, we get to the defender-attacker-defender. That is the next level. So I would say we can come back at 11:15. Okay. And then we can continue. And in the meantime, if you have any question, feel free to ask.
Well, I have a few.
Yeah,
could
go
you
ahead.
help me run the program, the ones we did, the one we did before? So if I type in include X run, it runs through. It gives me the feedback that is also
wait a second.
Moodle.
I just stopped the recording first. I pause and then. Okay, I think we can continue now. And the next topic, as I said, is the fortification. That means, how can we, as defender, do something before the attackers destroy the links? So now we can do something, fortify some of the arcs of the network. Then the attacker will destroy the fortified network, and then again we will maximize the flow after disruption. So let's see how we can do that. Actually, let's see how you will do that, because you have another activity just now. The idea is this. You now are the defender. Before you were the attacker, now you play the role of the defender, right? And you can fortify tau, I hope it's tau, I'm not good with the Greek letters, but should be tau, arcs of this network before the attacks. What do we mean by fortifying here? In this case, we mean that when an arc is fortified, then it cannot be destroyed later. So we make it basically indestructible. The question is, which arcs should you choose to fortify? Again, your objective as defender is that eventually the max flow is as high as possible, knowing that after your fortification, the attacker will destroy something else that is not protected, and then you have the max flow. In other way, fortifying arcs mean restricting the possible attacks of the attacker. You want to prevent him or her to do something to some of the arcs, so he can only do damage where it's not so impactful. That is more or less the idea. And of course, this number usually is small, because if you can fortify everything, then okay. But if you can only fortify a few arcs, then it's very important to choose wisely. Now you have an activity. Suppose you can fortify 4 arcs, okay? And your objective is to choose, as I say, the 4 arcs so that the max flow after the worst case attack is as large as possible. What you have to do, you have another run file called protection.run, and you should play with that. So let me show you this file. This is the file. Gamma is 3, is the number of arcs that the attacker can destroy, is as before. It still can destroy 3, but you can fortify 4. How do you fortify an arc? Basically, you have variable z. Remember the variable z that is what the attacker can do? Z equal to 1 means I destroy. We are basically fixing those to 0. So for every arc that you want to fortify, in this case we have 4 of them, we are fixing the variable z to 0, meaning the optimization cannot touch this number. It's 0 and it cannot be 1. This arc cannot be destroyed. Okay? So what you have to do is basically change these 4 entries inside the square bracket to reflect the arcs that you want to make indestructible. And your objective is to choose the 4 arcs such that when you run these, and this is based on the another mod file and data file, when you run these, the output will be the max flow after this protection, the worst case attack, and then the max flow. So it's the whole sequence.
We assume that the attacker has a lot of arcs that he can attack.
3, still 3.
Okay.
So this is the setting. We can protect 4, he can destroy 3. That seems an advantage for us, but it's not really. Because the number of choices, even if we, like, whenever we make a decision, then he knows that, right? So we don't know what he will do, but he saw what we did. And by knowing what we protect, he can then choose the best way to. So even if it's 4 and 3, protect 4, destroy 3, you will see that it's not so easy to find a solution where you can get high value. You may, I tell you, you may fortify 4 and then get the optimal solution is still 0. Meaning you can still reduce the flow to 0. For this one, because it's a little more challenging in a way, I give you 20 minutes. You can play with that. I leave to the screen again, maybe this one. Do I have the, yeah, this one. So you can have the pairs of nodes representing the arcs, and then you can put them inside the square bracket according to what you choose. Or maybe I can just show you this. This one. This was the worst case attack. maybe you can use this as a reference. This was the attack that was found when attacker can destroy 3. Okay, and in this case, again, the attacker can destroy 3. So I think we can, what is the time now? Is 23. Maybe we can come back at around 40 to, yeah, around 40 to 45. Let's see. And in the meantime, if you have questions, you let me know.
Yeah, I have one question now. So just to make sure I understand the assignment correctly, basically it's just manually playing around with the edge numbers, right?
Yes. So basically, let's say you have to choose 4, right? The idea is that you choose 4 arcs. Maybe you say, hey, this one, this one, this one, and this one. If I choose these 4, it means that every attack of the attacker cannot target them. So when you run the file, when you run the run file, the protection.run, and you specify these 4 arcs as protected, the code is trying to find the worst case attack where these 4 cannot be touched. And your objective is to find the 4 to protect such that the max flow resulting the attack is as large as possible.
Yeah.
Okay?
Okay. Yeah.
Okay, I think we can start again. And question is, which kind of results did you get? What was the objective function you were able to achieve by fortifying 4 arcs? And which arcs did you fortify?
I fortified 2 arcs from the source and 2 towards the sink.
Okay, so I guess you get your 20.
Yeah, so I also got 20, yeah.
Okay, you got already the solution, but just for you to know, many people may think that the best way is to say, well, if these are the critical arcs, the arcs that are destroyed by the attacker, I just need to protect them. And then I have another one. Actually, if you protect these 3, the green are protected now. If you protect them plus another one, then you see that the attacker will destroy 3, and still you can only send 10 units through this path. So you are right. This is not the best way, and the best way seems to be this. We need to guarantee that we fortify a complete path from the source to the terminal. So in this case, here, we are sure that we can send 10, and here we can send other 10. I also want to tell you something that you should consider. In this case, we have a simplified network in terms of size, and also we assume that every arc has the same capacity. But if you start to have different capacity, like 5, 15, 3, 29, and so on, then it's not as easy as you think to find the best option, right? So this was a simplified version because I wanted you to understand the logic behind, but in real cases, you need to run the optimization code because you cannot find by hand. So what are the considerations we can make here? Number one, protecting the arcs associated with the worst case attack, so the 3 red going out from the source may not be a good strategy. The arcs to be destroyed can change dramatically with the chosen fortification, meaning when we change the arc with fortify, then we are changing what the attackers will do. It can be quite different depending on the fortification. And it seems easier to find a worst case attack rather than the best case fortification. In this case, it was easy to find the fortification as well, but I think you start to understand the logic that when you have a real problem with more arcs, more nodes, and capacity that are different, it's not very easy to find the best case fortification. And if the network is large, so if you have to do this here, good luck. If I choose something like that and I choose one source and one terminal, and every link here is a different associated with a different capacity, you cannot. Probably at this scale, even the code I have cannot. It's too big. But just for you to know that in real cases, you need to run the optimization. Solving by hand is not an option. Now, the defender problem, right? What you did, if you remember before, with the attacker was the same. We say we cannot list all of them. Then you try, and then I show you how to do with the optimization. And then we use the trick to get the min max into a min, and then you solve an optimization problem, it's fine. So let's try to use the same trick as well. How do we find the best fortification? Well, as we did before, let's say now we have variable pij equal to 1 if arc ij is protected and 0 otherwise. Now the problem of the defender is this. So before it was min-max, minimize the attacker, want to minimize the max flow. Now we want to maximize the min-max. So this is called tri-level, is a defender-attacker-defender problem. And of course, we also have a budget constraint. How many arcs we can fortify was tau. How can then we say that an arc that is fortified cannot be destroyed with this? So remember, z is equal to 1 if we destroy. But if p is equal to 1, z is forced to be 0 because it's a 0, 1 variable. So with this constraint, we are saying that if ij is fortified because p is equal to 1, then z can only be 0. We cannot attack an arc that is fortified. So then the point would be, okay, I take all these constraints and variable and I put in the model, and then I do the same trick, right? So we say, hey, let's start with, this is what we did last time. The max flow was equal to the mean cut, and then min max is a min is a single mean. So then we can do the same, max min max, because of this transformation. This is a max mean problem, right? Because I know it seems like we are like max min max is confusing, but the idea is that this max min max become a max min problem because of this. Now the question is, can we transform again the min into a max and then we have the same? No, we cannot do it anymore. What is the reason? The reason is this. When we did a transformation the first time, this max flow is a linear problem, right? If it's a linear problem, we can use duality. But this problem here is not linear because we have integer variable. If we have integer variables, the trick of duality doesn't work anymore. So we cannot transform this into a max and then have a max. We cannot. Okay? And the reason why I repeat is because we have integer variable into this problem, the variable z, But here, we didn't have integer because if you look back at the model, variable f is a continuous variable. We have no integer here. So because of that, the resulting problem cannot be simplified to a single max. We need to keep this max min. We cannot do a further simplification. We have to work with this max min. But this max min is not a problem we can solve directly. So how do we solve this kind of problem? You need to develop an algorithm to solve that. I just give you the idea of the algorithm, not the details. It's not part of the course here, but just for you to know what is the logic behind. The idea is that you have an algorithm that plays the role of defender and attacker in sequence. So the algorithm is looking for the best fortification, okay, given a set of worst case attacks that found so far. And then when you have the fortification, you look for a new worst case attack. In other words, you are the attacker, you say, okay, I don't fortify anything. What is the worst case attack? You find it. And then you find a fortification to protect against that attack. Now that attack is not valid anymore. So with the current fortification, you as attacker say, okay, with this fortification, what is the next worst case attack? Now you take the two attacks found so far and you say, okay, I know that the attacker, first he was trying to do that, now he's trying to do this. What is the best fortification for these two attacks? And then the attacker will find a third one, and so on, until you reach a convergence where basically you cannot improve anymore. You basically reach an equilibrium, and this is the best solution. But you need to go through this iterative process, and every time you are solving an integer problem or a linear problem. So you're solving a sequence of this kind of problem, min-cap. And other problems, like this is to find the worst case attack, and to find the best fortification, you need to solve another one that I think should be linear. But still is an iterative algorithm. You cannot solve in one shot the whole thing. If you want to know more about this algorithm, you can look at these two papers we published. So this is an application to power grid fortification. And this is a more general paper where we apply this to any kind of network. And in this case here, you have also a smarter algorithm to solve this, but still you need to go through the iterations. Before we move to the final part where we try to see the link between what you have learned so far and resilience, is there any question? No? Okay. Okay, so I think at this point of the course, you have seen different ways to characterize resilience, right? And then you may be wondering, okay, what is the link with this optimization stuff that we have done in these two lectures? Okay, let's recap. In this case, we have a rational attacker and a defender. We have an algorithm available to solve the defender problem. That is the one you will find in the paper. We know that the defender can protect tau arcs, and the attacker can destroy gamma. And we also assume in this case that we don't really want the max flow at the end. We just need to guarantee some flow. What is the logic here? If, let's say, I want to protect my network, right? And I know the max flow in normal occasion is 30. Maybe I say, okay, I want to do the best I can with these arcs that I can protect, the gamma, my protection budget. Then I know there is an attack and I know I can maximize the flow. But if I reach, for example, 25 is good enough. I don't expect to be able to reach the best. Maybe I have some threshold, right? What is the challenge here? In the problem we had, we assume to know the attacker's budget. So the attacker can destroy 3 arcs, remember? But in reality, this is very unlikely to be available to the defender. Of course, there are many information that may be unavailable to the defender, like how much, like the technology that the attacker is employing, But definitely we cannot assume that we know the budget of the attacker. How much money the terrorists have to attack my system, I don't know. So how can I protect if I don't know how much they can damage my system, right? So in this case, we can use this challenge as an opportunity to define resilience in a different way. And this is the resilience definition using this model. In this case, the resilience is the maximum budget of the attacker, such that in the worst case, we can guarantee a flow above the threshold that we want. In other words, instead of saying that we don't know the attacker's budget, so we cannot do anything, we say, okay, let's try to use that as an objective function. That is our resilience. Let's see how we can make it as hard as possible for the attacker to push my max flow after attack below this threshold. So it's a different way to see resilience, because usually resilience is looking at what happens after an attack, what is the area under the curve and all this, but is rarely looking at the size of the attacks. Here, basically, we are saying we want to be able to protect against as many high impact disruptions as possible. Because if we maximize the budget of the attacker such that we can guarantee this flow, then basically we are saying make my system able to withstand attacks that are using as much budget as we can. Okay? So this basically summarized here. We are making as hard as possible for the attackers to win. If the attacker, let's say we solve this problem, right? What we can say is this: if the attacker budget, the real attacker budget is below R, then we know that with our solution, like the fortification P, with fortification P, we can always guarantee a flow of, sorry for my writing, at least this. In other words, I solve this problem, R is equal to 20. What does it mean? It means that, sorry, in this case, let's say R is equal to 2, okay? And this one is equal to 25. It means that every attack where the attacker can use up to 2, can destroy up to 2 links with the fortification that I found by solving the problem, I know that the flow cannot be below 25. And 2 is the maximum. So it means that if the attacker wants to push the flow below 25, it needs definitely to use more, destroy more than 2 links. And 2 is the maximum we can get. We can use any other strategy to find a fortification. We cannot find one where attacker may need to use a different value from 2. Like it needs to use, for example, the 3. No, this is the maximum we can find. Of course, the algorithm that I didn't explain that is in the paper is proof to find the optimal solution. So it's not an heuristic. Okay? So is this, I know it may be counterintuitive that to maximize the resilience, we are maximizing the attacker's budget. It's not that we are helping the attacker. Is that we want to make it as hard as possible. We want to make it as expensive as possible for the attacker to be able to win the game. That means push the flow below the threshold that we want. And in the papers, you will see a study where we try to study the relationship between this and this. So if this become larger, right? What happens is that we are more and more strict. So if we want a flow after attack that is larger and larger, of course, the attackers may need to destroy less to be able to win. And it makes sense, right? If we are very strict about the flow, if we really want a flow almost close to the optimal, it will be very easy for the attacker to win. But if we are more reasonable with this threshold, then for the attacker, it may become expensive, more and more expensive. And you can start to study the relationship, and some interesting results can be found. Like maybe there is a area where you increase this, but you're not affecting this too much. If you're more interested, again, you can have a look at the papers, and I can share with you if you are interested. But is it clear the idea of resilience here? What is the concept behind? And how this is linked to all what we have developed? Like, I hope you can see the logic from the first lecture, where we are ending, why we go through the max flow, the worst case attack, the defender problem, and how this is put together in this resilience definition. Okay, let's conclude. What have you learned in these two lectures? You have learned what is optimization, at least at a high level, the basics of integer and linear programming, how to use Ample and the solver simplex to model and solve linear and integer problems. Then you learn the max flow problem. You learn how to identify the worst case attack in a max flow problem using duality. Of course, I repeat, I didn't give you all the details, the mean cut, max flow, what is duality, and so on. But at least you have a basic understanding of the procedure. And then you also learn, and maybe this is one of the key messages, another definition of resilience that you may use when you start to study problems. Because again, resilience is a very general concept. Depending on the application, different ways to characterize resilience may be used. And then you have another one here based on optimization that in some contexts may make more sense than others. So you have another tool in your toolbox of resilience study to define, characterize, and solve problems where you want to optimize resilience. There are other resources. If you want to learn more about Ample and optimization, I put a course in my website. So there are a lecture when I go more into details of Ample. The two papers that I mentioned where we have applications of this procedure. And then we have my mail. So if you have any other question or you are interested to know more question about resilience, this kind of resilience, about Ample, about optimization, whatever it is, feel free to contact me. And with that, that's the end of the course, at least my side. I hope you found it interesting. And I think it's also interesting because not only for the resilience definition, but also because optimization modeling, at least the basic, may be useful for you, hopefully even later when you work or in many other situations where you can solve this kind of problem. A linear problem, maybe you have to solve a problem at work and you know it's optimization and you remember this course, you can go through the slide, write your Ample model and maybe find a solution that others cannot find. With that, I really thank you for being here. And if you have any questions, just feel free to ask.
Thank you, Alberto. Yeah, so if any question from you too, feel free to ask. You have Alberto's details. Yeah, on my end, thank you very much, Alberto. I share the recording with you also.
Thank you.
I do have I just have a question out of interest. I'm wondering, yes, at the center in Singapore where you work, do you mostly do academic research, so into like optimizing these kind of methods, or do you also are you also involved in more practical applications, like for the government, how to? Yes,
so it's a very good question because we have a mix of both. So just for you to know, the center, the Singapore ETH Center, is divided in 3 programs. One is called Future Cities Lab Global. Is a more, let's say, architecture-oriented. Then we have the Future Resilience System, where I work. And then there is another program that is more recent. It's called Future Health Technologies. They have different focus. We do research that is academic, like these papers are published as part of that center, and they are more academic. But then we also have collaborations with agencies. It's one of the KPI to work with local agencies, like the Land Transport Authority. We had collaborations with others, like we try also with the PUBs, the Water Authority. We have the URAs, the Urban Redevelopment Authority. And I have one where we publish a report this January with the defense. I mean, I cannot give you many details, but the idea is that they approach us with a logistic problem where they use robust optimization. So this kind of worst case ideas, and then we had them model the problem, and then it was another collaboration. So I would say that the focus of the center is on both. Both of them are important. What is the challenge? The challenge is that these groups working in these three programs are led by PIs that are professors. And the objective of a professor, especially when he's hiring a PhD, is to publish. And when you want to work with agencies and more applied staff, you may not be able to publish because the kind of work is different. So you always need to balance the trade-off between doing something with agencies and stakeholders that are looking at more practical stuff. That is a very strong request especially from the NRF, the National Research Foundation in Singapore. And on the other hand, balance the needs and the objectives of the PIs and professors that want to publish, that want PhD students to publish papers. They may be more academic and theoretical, and therefore harder to be translated into a practical collaboration. So that's a good question, because I think the main challenge we are facing is really to find this trade-off. But the short answer is yes, we do both of them. And if you want to know more, you can go to the SEC website. If you go to the FRS website, for example, we have a project working on even climate change modeling, cyber physical system, even the impact of like the social component, how is affecting resilience, so the role of people. And then we have the more like infrastructure resilience and maybe some optimization like what I do. So we have many topics, and the future health technologies is now using, just to give you an example, the digital tools to help people like senior, like predict the risk of fracture from the way they walk. A lot of cool things. So in this case, it's more practical oriented. They develop apps, they develop tools and software and things that people can use. For others like us, sometimes it's more theoretical, but again, we have both of them.
Thank you. Very interesting. I'll definitely take a look. I also had just one quick question for Helena, actually. Because we have the quiz next week, I think.
Yes.
So I was wondering if the lecture 5 slides will be posted still.
Yes. No, the session with Ying, right?
Yeah, it's a cyber.
Yeah. Okay, which one then? I will remind her. Yes. Okay, thank you for reminding me. I had asked him when I didn't hear. Okay, thank you. Yes, I will do. Thank you. All right.
Any other question? No? Okay.
Thank you very much.
Thank you. Okay, have a good day.
Thank you for attending, and I hope it will be useful for you.
Thanks.
For sure.
Thanks for the class.
Bye-bye.
Bye-bye.
Okay, bye-bye.